Hello, Integrated Math 1. Welcome to Module 2, Topic 1, Lesson 3. We're going to do the first half of it in this video, and then, of course, we'll do the second half of it for next time. So we've already been playing with our functions a little bit, plugging in numbers in the warm-up. We're playing with that. And also on our Getting Started activity, we were shifting our lovely little graph, our line up and down and doing things to it. And also we were multiplying things to it and watching what happened to our graph. So we're going to get a little more into that this week. So let's determine how translations, that shifting up and down, impact the graph of the linear function f of x equals x. This function, f of x equals x, is the basic function of the linear function family. And we call it a basic function because a basic function is just the simplest function of its type. So the simplest linear function is x, right? So f of x equals x is the simplest linear function around. So we refer to it as the basic function for our linear guys. It's just how it works. So we've already been playing with translations a little bit and noticing what happens. Let's look a little more in depth on what happens with our coordinates when we do that. So you can take the graph of f of x, our basic function, f of x equals x. This is our basic blah normal guy. It has a y-intercept at 0. Its slope is 1, right? We go up 1 over 1, up 1 over 1, up 1 over 1, or you could put a 1 in front of your x. So you can translate the graph of f of x down 5 units by moving each point 5 units down. So I could pick a point and be like 1, 2, 3, 4, 5, and do with the next point 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and just keep doing it for every single point on the line. And this transformed graph that we created, that we shoved down 5 units, we're going to call that m of x. So to translate the point -2, -2 from f of x onto our new guy, you can just subtract 5 from your output or y value. Notice that the input doesn't change. The input is still -2, that doesn't change. But the coordinates of the translated point, if I subtract 5, so that's the whole idea here, is that we actually, let me bring up my pen here. The idea is since it went down 5, I can just subtract 5 from my y coordinate, and that gives me a new y value of -7. But the x value didn't change. Same thing with the next point. We just went down 5, so I'm going to subtract 5 from my y and get -6. X value didn't change. Same thing here, -5. 0 minus 5 gives me a -5. -5, -1 minus 5 gives me a -4. -5. 2 minus 5 gives me a -3. So only the y coordinates changed. I just subtracted 5 from each one of them. The x coordinates didn't change at all, not at all. So when we shove it down 5 units, we're just going to subtract 5 from all of our y coordinates. So we have these 5 points here, kind of useful, kind of nice. So on a graph, it's easy to move it down 5 units. You just move everybody down 5 units. But even on a table, it's not bad because you can just subtract all the outputs, all of your y coordinates by 5. And that's really all you have to do. So with this in mind, I would like you to take a look at our m of x, at our translated function. You can look at the line on the graph. You can also look at your table. And I would like you to do 2 things. I'd like you to actually do 3 things. First, identify the slope of m of x, of our new function. Then identify the y-intercept of our new function m of x. The graph will be helpful for that. And then I want you to write the equation of the function in general form for m of x. Go ahead and hit pause, see what you can do with this, and then hit play when you're ready to check your work. So I started off by finding the slope. There are a few ways you could have done it. Remember that slope is rise over run. So I had to go up 1. Oops, that's not good. So I had to go up 1 and over 1. So that would be, means my slope would be 1 over 1, also known as, well, 1. Another way you could have found the slope, instead of doing rise over run on your little graph here, you could have used the slope formula here. You could have found, look, they're all in order, -2, -1, 0, 1, 2. Totally could have used first differences here. That would have worked as well. So you also could have found your slope by doing -5 minus 6. Oh, sorry, I'm going to try that again. -5 minus a -6. Hang on. I can fix that. So doing -5 minus a -6 over 0 minus a -1. Of course, this becomes a positive. -5 plus 6 gives me 1. This becomes a positive. 0 plus 1 is 1. Oh, look, my slope is 1. So you could have used either method, multiple methods here in order to find your slope. The point is that the slope is 1. For the y-intercept, though, I just looked at the graph and I was like, okay, well, where does it hit my y-axis? And it looks like it hits my y-axis, my y-intercept, hits my y-axis at -5. And that means I can write the general form of the equation, right? We usually write, so the general form is f, now we know it's f of x equals ax plus b. We know that that's my slope. We know that this is my y-intercept, except I can't write it very well. So fine, only it's not f of x, it's actually m of x. And so my slope is 1, my y-intercept is a -5, and I'm just gonna clean this up a bit. We don't usually write 1x, we usually just put x, and I don't need to put plus a -5, I can just put x minus 5. Yay, we found our form, our function in general form for m of x, hooray. So this is what happens when I translate my graph down 5 units. But what if you translate your graph of f of x up 5 units to create a new function which we'll call p of x? So I have a few things I want you to do for part A. First, draw p of x. Push f of x up 5 units. Then fill in the table for p of x, okay? You can manage it. Hit pause to work that out. Hit play when you're ready to check your work. So each of these points, I went up 5 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And one more point. 1, 2, 3, 4, 5. Ooh, sorry, that went wonky. I'll fix it. That's what erasers are for. So it was up here. There it is. And then I just connected the dots and I was like, boom, there's my line. It's so pretty. And of course, I labeled it P of X because I'm a good girl like that. And then I wrote the points. You could have just written down the coordinates for these points that you made on your graph. That would have been okay. Or you could have used that technique from before where you're like, oh, we're going up 5 units. So I need to add 5, add 5, add 5, add 5, add 5. X coordinates didn't change. No, they are the exact same. -2, -1, 0, 1, 2. But we're adding 5 to all those y coordinates. So now instead of -2, -2, -2 plus 5 gives me a +3. So -2, 3 should have been this point right here. If you add 5 on that y coordinate, you get -1, 4. Add 5 on this y coordinate, you get 0, 5. If you add 5 to this y coordinate, you get a point at 1, 6. And if you add 5 to this y coordinate, you get a point at 2, 7. And again, it should match the points that you made here. Boom, 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 boom. Yay. Yay, good job us. So now, you knew this was coming up next. So now what I'd like you to do is, just like we did last time with m of x, I would like you to identify the slope and the y-intercept for p of x, and then write p of x, the equation for p of x, for the function in general form. So once again, whether you use the graph and you counted rise over run, or whether you use the slope formula, subtract your y coordinates, subtract your x coordinates, either way, you should have found that the slope for p of x was 1. And if you were looking at the graph, you would have also discovered that your y-intercept for p of x was 5. And this means then that if I'm going to write p of x in the form of ax plus b, well, here's my a, here's my b. I'm going to plug those in. So I have 1x plus 5. I don't usually write 1x though. That's kind of weird. So I'm going to rewrite p of x as p of x equals x plus 5. We just don't usually put the 1 in front of the x. It looks funny. It's okay. It just looks funny. So hopefully you're noticing something here, that when we did m of x, we said m of x was translated down 5 units. And so we just took x and we subtracted 5. Did you catch that? That m of x equaled x minus 5? And look at this guy, our p of x guy up here. We said p of x got translated up 5 units. So look what happened. Instead of the function being x, the function is now x plus 5 because we pushed it up 5 units. There is a pattern happening here. It's not your imagination. So here's the deal. For the basic function f of x equals x, the transform function y equals f of x plus d is a vertical translation of the function. That if you take your function and you add d onto it, some number d, I don't care what d is, but you add some number d onto it, it gives you a vertical translation. It pushes things up and down. This translation affects the output values or the y values of your function, which makes sense. If we're going up and down, that's y, isn't it? That's not x. So that means that that d value, that plus d on the end, whatever number d is it's going to push your function up and down. It's going to affect the y coordinates of your points, your y values. And of course, you're smart enough to have already realized that if d is greater than 0, if your d value is a positive number, it shifts your graph up. If d is less than 0, if d is a negative number, the resulting graph shifts down. All right? Makes sense, right? If it goes up 5, I'm going to be adding 5. If I have a minus 5, it's going to be pushing it down 5 units. And of course, that distance that the graph is shifted is the absolute value of d, right? The positive and negative just tells us up or down. The number, that absolute value itself, that 5, tells us how many units we're shifting up or down. No big deal. Pretty nice, pretty straightforward stuff. So with this in mind, I would like you to just do a few more little things here. Looking back at f of x and looking back at p of x, and the functions you wrote for them, how did the transformation of the function affect the value of the function at x equals 2? So I want you to find f of 2, and I want you to find p of 2, similar to what we did in the warm-up. Go ahead and hit pause to work these out, and then hit play when you're ready to check your work. So I did f of 2 first. Well, we know that f of x is x. So f of 2 just means everywhere I see an x, I'm going to plug in a 2. So f of 2 is 2. Fair enough. Same thing with p of 2. Now, the only thing is p of x is now x plus 5. If I'm going to find p of 2, that means I'm substituting in a 2, and 2 plus 5 gives me 7. So it looks like my y value went from 2 to 7. So sure enough, this vertical translation increased the value of the function at x equals 2 by 5, which is what it should be doing, right? We know that it's going to increase our y values by 5. It's just what happens. It's what happens. All right, let's go for some next level stuff. I think you're ready for it. Here I have a new graph. I have j of x. Here on your graph, right? J of x, it's labeled j of x. You have this lovely line. They even graphed it for you. So nice of them to do. And here's what I would like you to do. First, translate the graph of j of x up 4 units and label that new guy as q of x. We call it the image. Label our image q of x. Then see if you can write q of x in terms of j of x. Go ahead and hit pause to work this out, and then hit play when you're ready to check your work. All right, so first thing I did is I was like, we got to move this stuff up. So I just picked some points, like I picked this point here, and it looks like I'm going up 4 units. So from this point, I'm going to go 1, 2, 3, 4. Here's another point. So 1, 2, 3, 4. You can pick as many or as few points as you like, but at some point you got to connect the dots. So I did that. I connected the dots. It said to label it as Q of X. So I'm going to label that Q of X. Yay, good job, me. Now here's the last trick. It's asking us to write Q of X in terms of J of X. Well, if I went up 5 units, that means I added 4 to J of X to get Q of X. So I'm going to say that Q of X equals J of X plus 4 because we pushed J of X up 4 units. So I'm just going to put a plus 4 on it. That's where it goes. That's what it does. Fair enough. All right. Do this again, only now I want you to translate the graph of J of X down 4 units, and I want you to label the new guy as R of X. Then I want you to write an equation for R of X in terms of J of X. So just like the last one, only now we're going down 4 units and we're calling it R of X. So go ahead and hit pause to work this out and then hit play when you're ready to check your work. All right. So first I'm going to push everything down and I'll do just like I did last time. I'll pick a point and I'm going to go down 4 units. 1, 2, 3, 4. I'll pick this point and go down 4 units. 1, 2, 3, 4, just straight down. Again, you can do as many or as few as you like, but at some point you got to connect those dots. Did ask us to label it as R of X, so I did that. And again, it says to write an equation for R of X in terms of J of X. Well, if I had to translate J of X down 4 units, that means I'm subtracting 4 from J of X. So fine, R of X equals J of X minus 4. Hooray. That wasn't so terrible, was it? The only thing is, these look weird, right? Q of X and R of X look weird because they have J of X inside them. So let's see if we can fix that. Let's rewrite J of X and R of X in terms of X. Let's make Q of X and R of X in terms of X. Let's make the J of X go away, and it's very easy to do because you know what J of X is, which means everywhere you see a J of X, you can replace it with 2x minus 1. Substitute in, clean them up, and see what you get. Go ahead and hit pause to work those out. Hit play when you're ready to check your work. All right, so I'm going to start with Q of X, which looked like this, J of X plus 4. And I was like, this is weird. So we said that instead of J of X, I can substitute in 2x minus 1. So I did. And now I have to clean it up. I have some like terms here, right? -1 plus 4. I believe that gives me a positive 3. All right, then. I can handle that. Let's do the same thing now for R of X. We said R of X was J of X minus 4. And we said having the J in there was weird. And so we're going to replace J of X with 2x minus 1. But I still have that minus 4 on the end. So fine, let's combine our like terms. -1 minus 4, that gives me a minus 5. And now I know that R of X is actually 2x minus 5. And I don't have the weird, these look more normal, right? These are now in general function form. They definitely look a lot nicer, a lot easier to work with. So what I would like you to do now is I want you to compare. So now you have all of this on your page. You have graphs for all these guys. You have proper equations for all these guys, right? You can see all of these lovely equations here instead of J's everywhere. I would like you to compare your equations and your graphs for all 3 of them, for J of X, Q of X, and R of X. What do you notice? Hit pause, write down your thoughts on what you notice, and then hit play when you're ready to check your work. So I don't know about you guys, but here's what I noticed, is that They all had the same slope. All of them had a slope of 2. They all had a slope of 2, right? They all had that 2x. So the lines all have the same slope. But the other thing I noticed when I was looking at their graphs, there was one other thing I noticed, and that was that they are all parallel. Did you catch that on the graphs, that all 3 of these lines were parallel to each other? Interesting to notice that you had the same slope and the lines are parallel on the graph. So in the previous activity, we're going on to 3.2 here, you translated the function j of x equals 2x minus 1 up 4 units to create q of x, right? Which ended up being 2x plus 3. So will the graphs of j of x and q of x ever intersect? And explain your reasoning, explain your thinking on that. Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check your work. So will the graphs of j of x and q of x ever intersect? Nope. And of course, the graphs of the functions will never intersect because they're always going to remain 4 units apart. We pushed q of x up 4 units. There's always going to be, because every single point had to go up 4 units, so they're always going to be 4 units apart. So no, they will never intersect, ever. Now, we were already noticing that these lines were parallel and that they had the same slope. So let's see if we can prove why that works algebraically. I know how much everybody loves algebra, right? So you can algebraically prove that a line and its translation are parallel to each other. You can totally prove that. So here I have line AB, and here are my coordinates x1, y1, x2, y2. I mean, they're not that exciting. I don't have numbers for them. And line AB was translated up A units. So it's a little a. So I was like, I'm going to go up A units, and I'm going to go up A units. Sorry for my super bad writing. To create line A prime, B prime. So when you see those little marks, we say prime. So A prime, B prime. So what I'd like you to do is take a moment, knowing what you know about translating things up. I would like you to identify the x and y coordinates, what happened to your x and y coordinates for the image. Go ahead and hit pause and put some thought into this, and then hit play when you're ready to check your work. So you know that if it's going up A units, that just means that that A is getting added onto your y coordinate. The x coordinate isn't going to change. The x coordinate isn't going to change at all. You're just going to add little a onto your y coordinate. So fine, the coordinates for A prime, and this is going to look funky, sorry. X1 didn't change, but my y coordinate is now y1 plus A. So of course, same thing happened to B, right? The x coordinate didn't change, but we are adding A units onto our y coordinate. So fine, the coordinates for B prime are x2, didn't change. And then our y2, we're just going to add A onto our y coordinate. It looks funky only because we are using variables instead of actual numeric values, but trust me, this is going somewhere. This is going somewhere. Stick with me. Can you real quick use the slope formula to calculate the slope of what we call the pre-image? So the pre-image is before the translation, so it's the original. So if you can't remember pre-image, it's cool. That just means the OG, okay? The original. So can you real quick use that slope formula to calculate the slope of the original of AB? Go ahead and hit pause and jot that down. Hit play when you're ready to check your work. So to find the slope, I need to subtract my y coordinates on top and subtract my x coordinates on the bottom. So I did. So the slope of my pre-image would be y sub 2 minus y sub 1, subtract my y coordinates on top, and then subtract my x coordinates on the bottom, x sub 2 minus x sub 1. Yay. We can't really do anything more than that. I can't simplify it because I don't have any proper values in there, just variables. So we'll leave it. It's funky, but that's okay. We still love it. You know what I'm about to ask you to do next, though, right? I want you to use the slope formula to now calculate the slope of the image. And remember, the image is the new guy, okay? So this is our new guy. Sorry. Oh, my goodness. Oh, my goodness. I lost my page. That's all right. I can bring it back because I've got skills like that. The image is just, hang on. Ugh, this is not working for me. My computer's being a punk. Hang on, I got this. So the image is just the new guy, okay? So in this case then, I want you to calculate the slope of this guy right here. Remember the points for A prime and the points for B prime? You remember what they are? We wrote them down earlier. Use those points to help you find the slope for the new image. It's gonna get a little funky, but trust me, stick with me, we can do this. Hit pause to see what you can do with it. Hit play when you're ready to check your work. So just real quick, our coordinates for A prime were x1 and then y1 plus a. Our coordinates for B prime were x sub 2 plus y sub, and then our y coordinate was y sub 2 plus a. So we said to subtract the y coordinates on the top, subtract the x coordinates on the bottom. So that's what I did. I took this guy, y sub 2 plus a, and I'm subtracting this guy, y sub 1 plus a. And then on the bottom, I'm doing x sub 2 minus x sub 1. Boom, boom. Yay. This looks messy, so I'm just going to do a few things. I'm going to drop the parentheses here. I'm also going to distribute that negative sign across these parentheses. So this becomes a negative y sub 1 and a negative a. And that looks better. And in fact, do you know what's even better? Do you know what's even better? Check this out. I have a plus a and a minus a. If I combine my like terms, my a's, a minus a is 0. They die. They go away. Oh. So now I have y sub 2 minus y sub 1 over x sub 2 plus minus x sub 1. Does this look familiar? Have we seen this somewhere before? I think that's going to help you with question D. Where question D says, how does the slope of the image compare to the slope of the pre-image? What do you notice about your answers on B and C? Go ahead and hit pause, jot down what you notice, and then hit play when you're ready to check your work. So I don't know about you guys, but I noticed they were the same. The slopes of the pre-image and image are, in fact, the exact same. Yeah, they have the same slope. They have the exact same slope. That should not be a surprise to us. We were kind of noticing the lines are parallel, and we kind of noticed on our lines that were parallel earlier that they had the same slope. So hopefully this is not exactly a big shock to you. So tell me then, how would you describe the relationship between the graph of the image and the graph of the pre-image? How would you describe how these two lines are related? There's a word and you know it. Hit pause, jot it down, hit play when you're ready to check your work. Yeah, guys, they're parallel. The graphs of the pre-image and image totally parallel, and we are very not surprised by that discovery because we kind of knew that was coming, let's be honest. So this is actually really interesting. So it looks like the slopes of parallel lines are the same. So if you have two lines that are parallel, you have the same slope. So this leads us to some interesting methods in order to find equations for parallel lines. So Jillian and Ramses each write the equation of a line that is parallel to y equals 1/2 x plus 3 and passes through the point 2, 9. So I want a line that's parallel to this guy and goes through this point. So here's Jillian's method and here's Ramsey's method. Now, both of these methods will get the job done. They will get the job done. And I'm going to explain both of these to you real quick here. So here's Jillian's thinking. Jillian says, I know that since the lines are parallel, the new line is just going to be a translation of y equals 1/2 x plus 3. She knows that this function is just going to get pushed up or down or something like that. She knows that's what's going to happen if they're parallel. So she decides I can substitute the x value, which in this case is 2, from 2, 9. So here's my new point. And she can substitute that x value into our function here, y equals 1/2 x plus 3, to determine the corresponding point on the pre-image, to find the original point. We know this is a point on the new line, but she can plug in that 2 to find the point on the original pre-image line. So she plugs in a 2. 1/2 times 2 is 1. 1 plus 3, or half of 2 is 1, I should say, plus 3 gives me 4. So that means the point that corresponds to 2, 9 on our original function is 2, 4. So originally it was 2, 4, but our new point is 2, 9. So going from 2, 4 to 2, 9 is a translation up 5 units. That means that she can take this function, our original function, y equals 1/2 x plus 3, and just add 5. And then 3 plus 5 gives us 8. So the equation of the parallel line is y equals 1/2 x plus 8. There you go. She found the new equation, which is what we were asked to do. Ramsey's did a different method, but it also works. It also gets there. So Ramsey says, okay, to write the equation of the line, all I need to know is the slope formula. He's like, the slope formula will get me there. So here's your slope formula. M equals y sub 2 minus y sub 1 equals all over x sub 2 minus x sub 1. Subtract your y's, subtract your x's. We know this. He knows what the slope is. Because the lines are parallel, he knows the slope is 1/2. We know the slope isn't going to change. And he also has a point, 2, 9, that he can substitute in for x and y. So here's what Ramsey's did. He said, okay, well, my slope is 1/2. So we replaced the m in his formula with 1/2. And then instead of y minus y, he wrote y minus 9. And then on the bottom, he wrote x minus 2. Plugged in his coordinates, his x coordinate, his y coordinate. And then it was time to clean up. So he did a little bit of cross multiplication, 1 times x minus 2, and then 2 times y minus 9. And at this point, we needed to get the y alone. So he divided both sides by 2. So if you divide by 2 over here, that dies, and we end up with a 1/2. Then he added 9 to both sides. So if you add 9, it pops up over here. And then he distributed that 1/2. So 1/2 times x is 1/2 x. Half of a -2 is a -1. And then he combined his like terms. -1 plus 9 gives us 8. And look at that! Ramsey's got the exact same equation that Jillian did. Yeah, they both found the equation of the line parallel to y equals 1/2 x plus 3 and passes through the point 2, 9. Both methods work, but here's my question for you. Which student's method do you prefer and why? They both work. They both get the job done, but can you just decide real quick, take a moment to decide which method you like better, why you like it better. Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to keep going. So I don't know about you, I like both methods. I don't know, I just like math. I like them both, but maybe you decided there was one you liked better than the other. That's fine. Do what works for you, because you're now going to need to use that method to help you write the equation of a line that is parallel to y equals -3x minus 1 and passes through the point -1, 5. You can use either Jillian's method or Ramsey's method to help you do it, but you're going to have to go through those same steps. So go ahead and hit pause, work your way through it, and then hit play when you're ready to check your work. So I used both methods. I did. So I'll start with Jillian's method, okay? I'm going to start with Jillian's method. For those of you that are Ramsey's people, don't freak out. We'll get to you in a second. So I started with Jillian's method where I was like, okay, I can substitute the x value from this point, -1, 5, into my function. So I did that. So I'm going to plug in a -1 for x. So y equals -3 times -1 minus 1. If I multiply -3 and a 1, I get a +3. Minus 1 gives me 2. So here's the deal. My original point then was -1, 2. If I plugged in a -1, I got a 2. But the new guy on the parallel line is -1, 5. So to get from 2 to 5, I have to translate up 3 units. So in order to do that, I took my function here, the original, -3x minus 1, and I just added 3. -1 plus 3 gives me a +2. So it looks like the equation of a line parallel to y equals -3x minus 1 that passes through the point -1, 5 is y equals -3x plus 2. For those of you that liked Ramsey's method better, I'm going to do that one as well. So Ramsey's method was using that slope formula, right? Like, yeah, so use the slope. We know what the slope is. We know the slope is -3, and we have points for x and y, -1 and 5, boom, boom. So I'm going to substitute in for m. I'm going to substitute in a -3. And then instead of y sub 2 minus y sub 1, I'm going to do y minus 5 over x minus a -1. At this point, I needed to do a little bit of cleanup. Don't like this on the bottom. I do know that the double negative becomes a positive, so I thought of this as x plus 1. And I did need to cross multiply. If it helps, you could even put your -3 over 1 if that helps you with your cross multiplication. So if 1 times y minus 5 equals -3 times x plus 1, double negative became a positive there. So just multiply, multiply. Well, that's nice. I now just have to get my y alone and then clean up the other side. So I'm going to add 5 to the other side. That's nice. So now my y is alone. Wonderful. Now I just have to clean up this mess because it is a mess. So let's go ahead and distribute that -3. So -3 times x is -3x. -3 times 1 is a -3. And now I'll just combine my like terms. -3 plus 5 gives me 2. So I still got y equals -3x plus 2. Both of these methods work. Both these methods get the job done. You can see we got the exact same answer. So use the one that works best for you. You can get there. As always, guys, I hope you found this helpful. I hope you found this useful. If you've got questions or concerns, please feel free to email me or stop by during office hours. I'll see you soon. Bye.